So today we will see how you can use a multi-layer perceptron to do the classification as well as additional regression tasks. So the first use case we are going to work on is diabetes, predicting the diabetes. So even before we go to diabetes, so you just have to know that in this particular use case we'll try different models and we'll see which one gives the best results along with multi-layer perceptron. So for multi-layer perceptron MLP classifier, so you can import it from neural network. Okay, and likewise you can import all other models from, so for example, if you want to import logistic regression, you have linear model, and then you have tree model for decision tree, random forest, XGBoost, and neighbors you have k nearest neighbors, and you have naive bias. From naive bias you can import Gaussian NB. Okay, so likewise you can import everything. So here what we are gonna do is we are gonna try to run the model on multiple number of training examples. So basically, unlike how we have previously done by looking at the exploratory data analysis, so we have to cultivate the habit of writing functional code, because that is how you would be writing the scalable scripts. So here we are just writing a function to plot the learning curves, and there we are specifying n jobs equals to 1, but I will use n jobs equals to -1, so that I want my model to use everything, basically all the cores in my CPU. Okay, and training sizes, so rest is just the definition of the plots, and estimator is the kernel, the actual model. Okay, so in scikit-learn we call it estimator. Estimator is same as the model that you're gonna call. So here what we are doing is we are gonna just using the parameters whatever we have passed and doing the plot. Okay, so you will see what kind of plots get plotted. And next is we want to also plot the confusion matrix, because it's a classification model, so we're gonna plot the confusion matrix. CM itself stands for confusion matrix, and whatever the classes are there, so that will provide and normalize, so some of the parameters that are there. So, and we are choosing the CMAP. CMAP means the style in which it has to print. So all these things are defined like X ticks and Y tick. X ticks means the labeling of the X label, X axis. Okay, what you should need, what do you need in the X axis, and Y ticks means what do you need on the Y axis. So all these things are printed, and now we are gonna compare the models. In while comparing the models, you have to define the names and models as list and results to capture the accuracies. In models you're gonna define all the models that you have imported before. Okay, you're gonna append all the things, and likewise accuracy results also you have to append. That's why you are appending to names here. Accuracy results we are gonna generate by running the model over a couple of results, not just a couple of runs, not just one run, but rather we're using the cross validation, and specifically 10 times we will run and take the accuracy and put it in that bucket. Then we'll do a box plot to see how the model and their accuracies rank up. Okay, and then we are also just for each of these that we have defined. So basically define in definition models, I think we are not using, that's why we are just printing it. We are printing the names of it. Next is names you have, classifiers you have, and dictionary characters you have. All right, so let's run this. I think I already have. Okay, So let's look at the data first. So the data looks like, when you import the data, so it looks like this. You have information on various features, and outcome is what you have to determine. 1 means the person has diabetes mellitus, 0 means they don't have diabetes. Okay, so this way you have the information, and basis on this you're gonna do the plot also. Here we are plotting the, notice whatever the feature we are passing here above, that only we are gonna do a dist plot. So when we are calling the outcome is the actual hue value. Okay, and next is we are plotting insulin versus diagnosis. Okay, so this we are plotting. So blue means healthy, what a healthy person looks like, how much insulin they are producing, versus orange who has diabetes. So as you can see, you can't really tell from this data whether, looking at the different insulin levels, you can't tell whether the person is diabetic or not, because even the non-diabetic patients will have the same amount of, as you can see, blues are going till here also. If you, the same thing, you can't look at the skin thickness and say whether a person is diabetic or not, because as you can see, even here blue bar is there. Okay, so this is, I think you can't tell just like that, but you have to do proper thorough analysis. So if you randomly choose the data, this is what the data looks like. Okay, and here we are trying to see how many null values are there. Okay, null value percentage, how many values are missing, and here also we are just taking the count. So totally we have 768 rows, but out of that, in this particular feature, 111 rows are missing, glucose is missing 5. So if too many are missing, then probably we have to look at the percentage. So as you can see, 14% we can impute, 4% we can impute, 48% is missing in this. So that's very difficult to use that feature. But anyway, because insulin is required for this particular use case, I think we will try to do a imputation. Next is, we have found out that 50% of the patients did not have insulin levels measured at all. Okay, so that you have to handle. Anyway, so that I would prefer that we still go ahead and do the imputation based on the mean. Okay, next is we are looking at correlation, which feature is having higher correlation. So as you have already known, right, that every time you call a data.core and on top of that you got a heat map, automatically it takes the Pearson correlation. Okay, so this I think we have not discussed before, but we at some point we have to discuss anyway. See this happened. Okay, give me a minute. Okay, so when you something anyway, so when you see this, okay, correlation method, Pearson correlation is used. Actually there are 3 different methods of correlation: Pearson, Kendall and Spearman. So Pearson correlation is the standard correlation coefficient. Okay, it is used when the relationship between the variables is linear, but that is rarely the case, right? So if you do, I think it will take time, but still let's run. SNS dot pair plot. If you do a pair plot of, it will give you the relationship between the various features. So here I would type dataset. Okay, so let it run, we will see later. So what I'm trying to say is, first make sure that you, okay, now you can see here this shows the data is moving in one direction, so we can say it is linear in nature. But here you notice it's very how do I put it, very random. You can't tell the relationship at all. Okay, here it is kind of values are there, value based. Okay, so looking at the pair plot, you can't tell what type of relationship exists in the data, and hence I would recommend that when every time you run this data correlation, change the method once, run it default once to see, identify what type of relationship exists. But here go ahead and change the method once. So for example, you have Kendall or Spearman. So Spearman is used for non-linear relationships. It can handle both non-linear as well as linear relationships. Okay, so I would like you to change the correlation method. So just pass method equals to Spearman. Okay, and try plotting it. So here you can see it is also going from 0 to 1, here also 0 to 1. Okay, notice the differences for pregnancies versus blood pressure. Pregnancies versus blood pressure, see it is 0.19. okay, there it is 0.14. so there is a slight difference in the calculation. So here notice this is web. So basically when Spearman R is calculating, it is kind of making certain changes in the data and calculating. In between Pearson and Spearman, I would choose Spearman, okay, for its accuracy. So using this, now you can choose which features are showing the correlation. So the idea is, if your correlation is closer to 0, they are not good features. If your correlation is towards 1 or minus 1, okay, then you can choose those features. Okay, for example, age with outcome. Okay, basically do one thing, look at the last row. So glucose with outcome is a good predictor. Okay, and likewise insulin, you notice insulin actually it's very close to 0, it's not a good predictor. Next is 0.31. BMI is a good predictor of diabetes. Age is a good predictor of diabetes. It's somewhere here, 30% of the time it's able to predict. Okay, so that is one. Second thing is, you also have to start looking at the correlation between each other. So as you can see here, age, which ones do we say, 0.54, insulin with skin thickness. Okay, so they have certain amount of correlation. BMI with skin thickness has a certain amount of correlation. Okay, so this way you can identify and choose to drop or keep the features, certain features, which you will see, which we do later on. So this is just for understanding what they look like. When you plot, you're just doing the same thing above what we have done, but it's just in values. Okay, next is, now if you see insulin, the same thing we saw, what we saw above. We noticed that insulin was missing 50% of the data, right? So we have various imputing methods. Okay, we have to choose the best imputing. Here we are choosing something called simple imputer. Again, don't worry about the feature engineering, like I have told multiple times. I will conduct a separate class for that. But when it comes to imputing is nothing but replacing the missing values with some other value. Okay, so here what we are doing is, we are imputing missing values wherever you have 0, and we are choosing the strategy as median. That means we are gonna use the median of that particular feature to do the imputation. Okay, and that is being applied for in the entire X train, wherever X train is there with the entire data. So for that we have already split it, the data. Okay, once we have split it, we are doing the imputation for both. And once you have the data set, now we are trying to analyze how much of data here. It's not, it has replaced I think most of the data, so hence it's not printing the orange part. Okay, no, it is printing, but it's just that we have deliberately made it as none. Okay, we just want to look at the only insulin part of it, not the people who don't have insulin, but rather the healthy people. Okay, why are give me a second. So I think we have to also look at insulin and skin thickness outcome. Okay, fit transform. Okay, all right. So let's do one thing. Insulin. Let's do insulin. Okay. Here let's do skin thickness. Okay. So 4 is being called, and okay, we have defined it as in dictionaries. Okay. We have defined it in dictionaries. Labels equals to 4 we are calling insulin, fine, but we are not using the hue. Okay, let me feature label value. Okay, one moment. So we'll have to also include the outcome. Okay, let's try outcome. Outcome is not there, we have removed outcome. Okay, outcome is x train I'm using, fine. X, okay, x train is removed, so that's why. Okay, from the diabetes you're removing the last column, so x train is not available, but it's available in y. So if I use y train of outcome. Okay, y um description, outcome. Outcome name, what have we named it? Data dot y. Okay, just 1 second. Y doesn't have, oh, it has the name as outcome only. Y train of outcome. So why don't we try like this instead? Y train. Okay, shape mismatch. Fine, the amount of data that is being used, it has a mismatch. Okay, okay, all right, no worries. So we'll do one thing. For now, we'll use the hue as none only. So basically, what you see here is both um, both healthy and non-healthy, both healthy and non-healthy. But it's just that we are not splitting the data basis on hue factor. Okay, so this is what the data looks like now. As you can see, because we have chosen median, most of our data is concentrated on the center here. So that's why you see these long bars, because of that only, because we have chosen median for imputation. Um, Likewise, we are just selecting the labels, we are just testing few things. Okay, actually I have try to replace the nan values, but again this kind of just ignore this part because this is not doing much. Okay, just understand that we are trying to get the labels of it and try to see how many um, values are zero now. Okay, as you can see, everything has been filled, so none of them are zeros. Now is the time to evaluate those models. Whatever we have called in the names and classifiers, we are gonna compare them. Try to compare and calculate the mean as well as standard deviation. Okay, and when you do that, when you run the call the function, okay, define models is the function, and when you do this, you'll get the comparison. As you can see, MLP multi-layer perceptron is able to give 71% of accuracy. Okay, with 0.05 as the standard deviation. Although there are some other models which are performing better, like these two. Okay, but still MLP is able to gives the results that you can see here. Multi-layer perceptron. Okay, so whatever you see here is the accuracy range. Okay, this accuracy is ranging from 0.625 to somewhere around 0.80, and the mean is 0.77 something, 71 or something. Okay, so this way you can use the MLP model, MLP classifier. Now so this is not even the usual way how we use multi-layer perceptrons. This is what I wanted to talk about today. So this is what you see here, a multi MLP classifier that we call, is the very old way, I would say, of using the multi-layer perceptron. The actual way we use it is using keras, that I will show you. But for the sake of understanding, because we are working on this data set, we have gone ahead and used decision tree as well. Okay, so decision tree classifier has given certain results here. Okay, so we want to analyze that, and on top of that we want to analyze the XGBoost, which is not seen here in this. Okay, so what we are doing is we are just doing the model fitting, the same usual thing, doing the cross validation score, predictions are calculated, and confusion matrix is plotted. Okay, when you do that, as you can see, decision tree so score seems to be high, but for validation the score seems to be low. This is a typical case of overfitting. It is 100% overfitting. Okay, it's learning the training data set very well, not doing well on the test data set on the green. Okay, so likewise you have confusion matrix, as we have already talked about this. So these are two positives, okay, and two negatives, false positives, false negatives. So this way you can also calculate the recall and precision. And because we are calling the plot decision tree function here, okay, we have to use something called graph base, which will allow us to visualize the tree based structure. This again we'll talk about it in decision tree. So this is what it looks like. The decision tree is able to come up with its own rules and divide the data. So glucose, what it's doing is it is considering 127.5. basis on this it is dividing the data. Okay, so this way it will divide and tree structure is formed. And likewise you can calculate the feature importance for decision tree. When you do that, again I'm trying to do it for both random forest, decision tree, as well as XGBoost classifiers. For various things we can know the coefficients, which coefficients are giving us the best results. For example, glucose is giving the best result. I mean, it's trying to predict the diabetes levels. Here also glucose is the prime factor, and BMI and age, top three factors. Here glucose, BMI and age. Here also glucose, BMI and age. Okay, so this is what we have done. But this is, like I said, this is not the actual way how we actually build the neural network based models. The actual way is something by using something called keras. Now keras is a library that is integrated into multiple other libraries like pytorch, tensorflow, jax, openvino, and this is a library that is used very extensively. If you are going to use deep learning NLP based deep learning based NLP models, you have to know keras. Okay, so as you can see, this is very scalable, highly scalable library. Okay, it can scale to large clusters of GPUs or even TPU pods. Look who is using these libraries. The original developers are also happen to be top-notch people. CERN, NASA, NIH are using this, and this can scale at exa level. Okay, exa scale scalability. So that's one of the advantage. Now, this how do we use it is the question now. Okay, very simple. I will only talk about the skeletal part of keras. Okay, just to give you a brief idea. So when you look at a neural network model, you will see that it has input layer, it has hidden layers, and then it has output layer. Okay, so we have something called sequential. So basically sequential API allows us to define things in sequence, one after the other. So when you call sequential, which happens to be called from the keras models. Okay, so you can call keras sequential API. In sequential API, you can pass input layer first, because that's what comes in the neural network, right? So input layer, you can define input layer as dense layer. Now you can go ahead and start adding the layers. I will come back to dense layer, but I'm just saying you can add the layers one by one. Dense layer is nothing but it's a fully connected layer where every neuron is connected to every other neuron. Okay, that is why we call it as dense layer. Now dense layer, you can define how many neurons you want. Here I'm defining 64 neurons I want. And what is the activation? We already talked about this activation function you have to define. And what is the input shape we have to define. So this will become your input layer. Okay, so this way you can define the input and add that input layer to the model. After adding the first layer, then you have to add the second layer. Second layer also you can be added just by calling model.add. Here they are adding the image based convolutional layer. Okay, but in our case for a multi-layer perceptron, we will be adding something else. Okay, very simple sequential layer will be adding. So likewise you can keep on adding how many you want, you can add, and how many neurons you want, you can keep on defining. Okay, so multiple neurons, multiple layers you can define, and finally you can define the you can compile the model. While compiling the model, okay, compiling is nothing but executing the model, fitting the data. Okay, there you have to define the optimizer, the same solver that we discussed, right? Adam Blackline, if you remember from yesterday's class. So that optimizer we have to add, and we have to define the loss function. What is going to be our loss function? Nothing but mean squared error, root mean squared error, whatever it is, you have to define it here. And what are you going to measure? You are going to measure accuracy, or what exactly you are going to measure, so that you have to add. Okay, so very simple. I'll repeat. You have to define the sequential layer, define the input layer, add the input layer, add how many hidden layers you want. So, okay, finally you can compile it. Okay, next, after you compile it, you have compiled only, you have not yet executed. Then you will call the history. You will assign it as just history. Now this you are doing to print the results. Okay, up until this point you have defined everything that is to be used by the model, but now you have to also define what is your data, how many times you want to run. Epoch is nothing but complete run of whole data, training data, and what should be your batch size, and what should be your validation data. So that you have to define. Okay, additionally you can also define callbacks. In callbacks, you remember yesterday we talked about early stopping, sorry. In early stopping you can define the patience level. So all of that you can do. Finally, To evaluate the model, you just have to call evaluate model, just like how we call model.predict. You have to call model.evaluate, and you can also choose to call model.predict, one of these two. Okay, and early stopping, like I was saying, this also can be added. That's all there is. So there is only sequential, model dot add, model compile, okay, and then model fit, okay, and then if you want to do predict or early stopping, that you can do. That's all, 4 to 5 steps only, and these steps are repetitive. Okay, most of the time they'll be repetitive. Let's um, go back to what we were doing. So one moment. Okay, fine. So we will look at how to use this MLP using Keras now, because what we saw was the just the old fashion of doing things. Here what we are gonna do is we are gonna use Keras from TensorFlow. Okay, so Keras is now inbuilt into TensorFlows. Here we are gonna use layers and callbacks. Callbacks for early stopping. Layers is I'm gonna use layers to build various layers now. Okay. First thing is, okay, I'll come back to this reduced memory usage. First thing is how to build the how to use the sequential API and build the various layers, that we will see. So basically, as you can see, if you want to build a layer, all you have to do is call this sequential API. Sequential matlab it is allowing you to build things in sequence. The first sequence is input. Okay, input layer. Here we are not exactly specifying input layer, but you can just pass the shape. Here I'm passing the shape of the input. Next is I'm defining the layer. So how many layers I'm defining? So this is my first layer, second layer, third layer, fourth layer, okay, fifth layer. So I'm defining 5 layers, and on top of this there is input layer, which I have not defined, but I'm rather passing it as shape. Okay, so there are totally 8 layers now. Input layer, which I'm passing through this one, first hidden layer, second hidden layer, third hidden layer, fourth hidden layer, and finally the output layer. Okay, so this is our output layer, and we are using the activation as softmax. Yesterday we discussed this. Softmax is used for multi-class classification. Okay, sigmoid is used for binary classification. So softmax can also be used if you have two different outputs. Okay, so here dense layer has, last layer has 7. That means 7 outputs basically. That is what we are signifying. But for binary classification, use sigmoid also. Okay, so talking about these numbers, in my second layer, input layer, I have already defined. In my second layer there are 600 neurons, here 300 neurons, 150 neurons, 750 neurons. Notice how I am decreasing the number of neurons. Okay, finally I am reducing it to 7. Okay, these numbers are not it is not necessary that you use 600. Here you can use 100, 50, 25, okay, 12, and then you can reduce it to 2. That way also you can do. Okay, in case if I had to run this same model on diabetes, then I would have rather used, in input layer I would have used how many ever features I had. For example, I had 7 features, or so how many, 1 2 3 4 5 6 7 8 features I would have used. Here I would have passed the shape as 8. Okay, and in the next layer I would have used, let's just say 10. Okay, then 5. Okay, then I would not even have used so many dense layers in the first place. I would have used only 2 dense layers, sufficient. Okay, so I would have gotten rid of these two. I would have used 8. Okay, maybe 6, and or maybe 5. 8, 5 I would have tested. Okay, because there is no hardcore rule on how many to use. Basically, whichever gives you the best result, you have to keep trying, trial and error method. Okay, so first I would have tried with 8 because 8 is the input. I need 8, and output is 2. So I need 2, and I would have replaced this with sigmoid because I needed 2 only. And whatever it comes in between, you can test it with various numbers. Next, here also activation celu is just very similar to relu with minor change. I will come back to celu as well, but for now just understand celu is another activation function. So you have to define activation at each layer. That is what I'm trying to say. At each layer, what is happening? Remember that equation, w into x plus b equals to y. Okay, or in other terms, y equals to mx plus c, the same linear equation formula. Okay, that is what is happening. So here, whatever the data you are providing, x value, okay, and x is nothing but first row of data you are providing. For that first row, you're gonna use w, you're gonna multiply with w to arrive at y. And how do you know w? This initialization, Lacan normal initialization is another type of initialization, just like how your HE initialization or Glorot initialization that we discussed yesterday to randomly or pick some values of w to start with. So that is what is happening. Randomly you are picking the values of w, okay, and multiplying with x and adding some bias that model will automatically handle, and equating it to y value you already have, either it is diabetes or not diabetes. Okay, that is what is y, either it is 1 or is 0, that you are equating to this value, and activation is happening there. Wherever the values become negative, they are made as 0. Wherever values are positive, they are retained. Okay, these calculations are happening at every layer. That is what I'm trying to explain. At each layer, these calculations are happening, and activation is filtering out those inputs, and likewise back propagation is happening. See, in the first run, first is it will forward propagation. Forward propagation will happen. Okay, first it will do all these calculations, pass the data to the, it will then normalize the data, it will pass to the next layer, then normalize the data, pass, normalize, pass, normalize. Okay, the moment it comes here, it won't go here, rather it will go back again. Now back propagation starts. Now once you have the data here, back propagation will start. What is back propagation? Back propagation means you're changing w with delta w by multiplying with alpha, okay, and subtracting from w only. So this is very small value. Let's just say initially w as 5, you are multiplying, this is anyway small value 0.01, and delta value is the differentiation of w, nothing but dw by, okay, this is dw, you're differentiating w and multiplying it with this and subtracting from this. Now from 5 the value might go down to 4.5. okay, so that is what back propagation is happening. Back propagation will happen here, and then here, then here, then here. The moment the values come back to this place again, back to the first layer, again comparison is happening, y to y dash, loss function is being calculated, and if the loss has reduced, if it has not reduced by much, okay, then again next pass happens. So whatever happened in the first attempt, that is forward propagation, forward propagation, forward propagation, and then back propagation. From forward propagation to back propagation, we call it as one epoch. Okay, all the data is fed, passed, and then brought back by using back propagation. That is one epoch. And further, if the loss function has not decreased, loss has not decreased, again the next epoch happens, the data again goes back, okay, again comes back forward and back propagation. This way it repeats how multiple number of times, whatever the number of epochs you have defined, so many number of epochs happen. So in this case we have defined some 100 or whatever the number, so many epochs will take place. Here 200 we have defined. So you will see that the data gets so many times the calculations happen. 1 second. Okay, all right. So we'll talk about leak on normal initialization. This is just another type of initialization that is happening. So did you understand how to define a neural network layer using Keras? You just have to keep calling the layers, okay, one by one, and you are free to test with so many, whatever the number of neurons you want, you can test it. Then you are calling the model compile. In the compile you are passing the optimizer, and loss also you are describing, and what do you want to measure, accuracy or some other metric that you have to define. Okay, and once you do, you can go ahead and predict. You can do the prediction part. Here I'm running it for multiple runs, that's why you're seeing all of this. Okay, and so you have to predict, and once you predict, you can print the accuracy. As you can see, actually this code is still running. It's been running from the morning. I started at 5 a.m. and the reason is because of the data. I will show you what I'm trying to do. Anyway, so did you understand the structure? At least if you understood the structure, we can use this API now. Okay, so here what we are doing is we have a data set called tabular playground series. Okay, so for this data set, basically we are trying to understand what type of playground it is. So more information on this data set is available. Okay, you can go through. I have attached the links. You can go through and you will understand better. So look at the training data set. Look at the size, 522.6 MB. The data alone is 500 MB. If I manipulate and if I do some computations on that data, it will easily eat up my 16 GB of RAM. Okay, easily it will eat up my RAM. So every time when you're dealing with high amount of data, okay, you have to take certain steps. One of the steps is, there is a very beautiful article already written on this, okay, by this person Bex T. So his ways are very simple. What he is saying is, when we use pandas data frame, the data type, okay, the data type that we use, those data types alone eat up a lot of memory. So what his solution is very simple. Instead of using pandas data frame, which is like which uses these Python types, okay, pandas data types are what? Object, int 64, float 64, bool, date 64. This is what the pandas data frame are, right? What his solution is, let's not use pandas data frame, let's convert everything into NumPy data frame. Anyway, they are similar to arrays only. So let's use NumPy types. This way you can compress the data by 80%. Okay, and when I went through this article and used his approach, I was really surprised. My data also reduced by more than 80%. So I will explain what we are trying to do. When you have huge amount of data that you want to work on your machine locally, what you have to do is, we are defining the numeric types that we want to convert, and we are calling this memory usage function. Okay, and for memory usage function, okay, wherever the memory usage function is high, what we are saying is, we want to, okay, convert as type we want to take that column and convert it into as type of np.int int 8. Okay, so wherever the column has, you can simplify this code. This is code written, I mean, too many things are happening here, but the most important thing is this. What we are saying is, wherever the d types, okay, wherever the d types are pandas d types, you just convert that column into numpy.int 8. Here numpy.int 16. Okay, likewise you convert into equivalent numpy d types rather than pandas d types, and the same thing for float also, float 16, float 32. Okay, when you do those and you again start calculating the memory, initially you calculate the memory, okay, before conversion. After conversion you calculate the memory and you print the percentage of the amount of memory reduced. That is what we are saying. When we run this code, okay, notice initial memory was 259 MB, it was reduced to 63.90 MB, which is 84 reduction, 84% or 85% reduction in the memory. And this you can confirm when you run this. Initial data was 500 MB, now you have 259 MB. Okay, so this is what you can confirm. And notice how many rows are there in the data. 4 million rows of data is I'm working on. That's why maybe perhaps the code is still running. 4 million records, that is 40 lakh records are there in the data. Okay, and when you have huge amount of data, you can't use classical ML most of the time. Why? Your logistic regression won't may not be the right one. Why? Can anyone answer why logistic regression cannot be used on 40 million records? I'll give you a hint. Solver, LBFGS, liblinear. Nothing? Ringing the bell? Okay, all right. So one of the assumptions of the logistic regression is, see, the data should be a small data set. Why? Because there is a complex optimization algorithm running underneath. Okay, so you can't use logistic regression. Calculation of Hessian matrix, how will you calculate Hessian matrix for 40 million records? That's gonna take forever. Okay, so logistic regression is out of question. Perhaps maybe you can use a tree based structure, but there also you have to understand number of weak learners that are being used are high. Okay, you have to set it high in order to capture all the complexity in the data. That also is going to take time. So in such cases, because we have too much amount of data, this is a best use case for neural networks. Neural networks need huge amount of data and they work quite efficiently because there is not too many things are happening, so just dot product calculations. So this might be a better use case suited for neural networks. Okay, so we are reading the data, reducing the memory. After reducing the memory, we are looking at the information what we have now. As you can see, all the data types have been changed. Now you have 55 rows of data. I will ask you another question. Okay, logistic regression cannot be used. Tree based structure, my tree based algorithms might work, might not. Can we not use KNN? In this case we cannot because there are 55 columns. That will suffer from curse of dimensionality problem. Okay, so if there are too many features, we can't use KNN. This also we have learnt in the KNN class, if you can recall. So that's why we are not using KNN also. We are directly going to neural networks. So once you have the information here, you're trying to describe. Now I can't describe the information for 40 million. That is absurd. Okay, so what I'm gonna do is I'm gonna do a selective chunk and describe. Small sample I'm selecting, I'm doing the describe, and that too I'm selecting only certain features, certain columns. Data I'm choosing as is 40 million records. Okay, this we have discussed in data selection, ILOC. Okay, anyway, so in data analysis I think we have learned this part. So you're choosing the chunk of the data, describing it, and now you can go through the various describe factors where there are too many outliers, where standard deviation is minimum, which features are showing the skewness and all of that. Okay, next is we are looking at the value type, cover type. Okay, one second. One moment. Okay, so this is what it is. Basically, the data set itself has information on, let's look at the data set description. Okay, so basically, as you can see, what exactly we are trying to do here is, we are trying to, where is that part? So basically we are looking at the data, tabular data, not the image. Don't look at this image. So we are gonna look at the tabular data. In the data there are a lot of information. Okay, basis on that we are trying to predict what type of congestion there is. Okay, congestion levels. Okay, so that is what the data set is about. Okay, whatever you are seeing here, that is what it is about. So I just wanted to clear that. So cover type is something that we have to predict, and I think that data set is different. Anyway, fine. So we have the information on elevation, aspect, slope, hillside, soil type, etc., etc. So basis on that we have to choose the cover type. Now you're gonna, that is what we are looking at here. So there are 7 cover types. This is the reason why we have 7 different neurons in the output. Why? Because there are 7 different cover types. Okay, and as you can see we are dropping certain features because um, basis on this, ideally we should have tested tested the data and checked, but anyway, so just understand that we are not going to use these two. I should have checked this why we are not going to use, but anyway, so for now just we are consider we are going to use only 53, and because we have splitted the data, we have already splitted the data into x and y. That's why we are gonna see x we have already defined here, y we have already defined here, and we have also label encoded the y values. That's why we are deleting this. Why? To free up some memory. It's a huge data set, no? So that's why we are deleting here. And Python's automatic garbage collection will free up that memory for us. So various different configurations are already tried. For example, 64 layers of all the 64 layers, 5 layers of 64 neurons are already tried. Okay, and other configurations like 150 neurons, 70, 47. So these are also tried. 150, 70, again same things. Okay, with different values. Okay, mainly the initialization part. So between these two they are already tried, and we have made a note of the accuracy here. Okay, likewise here, kernel is HE normal is used there. In the above part, Lacon normal is used. So various different configurations have already been tried. Now we are gonna try a different one. So for all those configurations what we have obtained is 96% of accuracy is what we have obtained. Okay, so here we are gonna try the new configuration. The first thing is we are gonna define the stopping criteria. I want to stop if I am not gonna see a improvement in 10 consecutive epochs. Okay, let me make it 5 because it's a huge data set, we can't afford to run for 10 times. So how many epochs do you want to wait before stopping? That I am defining as patience as 5. Okay, minimum change, how much minimum change are you expecting between each iteration? That you are defining. Next, what do you want to measure? In this case, we have splitted the data into training set and validation set. So I'm going to monitor the validation accuracy only. Okay, so these are all my stopping criteria, and at the end I'm saying restore whatever are the best weights that that have been calculated during the various iterations. You store those and restore finally the best weights. That's what I'm saying. Okay, this early stopping will be used when we define the models. Next is we are using the callbacks again. For the same callbacks we are adding additional criteria, wherein which we are using this function reduce on plateau. I'll come back to this. So we are using this another criteria, and where we are monitoring the validation loss, and we are defining certain. Here also I would rather want to have patience as 5, and minimum LR and factors are defining. Nothing but lower bound on the learning rate, how much lower bound you want to have. Okay, and number of epochs and factors basis on which the learning rate will be reduced. So all these things are defined. Next is how many epochs. 200 epochs is too high. I would rather want to keep it as 100. Batch size is for 4096. Now batch size becomes very important in this case. Why? Because you have 40 million records, and if you give this number too small, like 16, it will take forever for the model to run. Okay, that's why I'm gonna choose whatever the maximum number in multiples of 2 possible, and how many splits you want to define. Okay, that also you can be defined. Now you can start building your model. There are two different ways also to build the model here. Okay, one, you can define Keras model is equal to Keras dot sequential like this. Okay, here I will type model equals to Keras dot sequential. You can define first. Plain model you can define, and then you can start adding the layers to it. So how you do the same thing is, you can define this multiple times. Okay, now you can choose to define here as 600. Okay, here 300. I'm showing both the ways of doing this. Okay, so this is 150. Here you can choose 75, and finally you want 7. You can choose provide here as 7. Here you have softmax, so you can change the activation to softmax here. Rest you want to choose whatever you want to use, celu, so that you can choose. And Lacan normal also you can keep as is. You don't need Lacan normal for the last one. You are not gonna use the activation. So this way you can define the code. This is one way of defining, and this is another way of defining. So what I'm gonna do is, instead of defining separate layers, I'm taking everything and putting inside this sequential in the brackets. Okay, if I put it inside these brackets, that is what you see here. See, this is the bracket. You defined everything within that bracket. Now when you want to define everything in the bracket, you don't have to call model multiple times. Rather you can use layers.dense here. Okay, just this part. You don't have to define these. You can just call these much, layer.dense. So this way you can define. So that is what you see here, layer.dense, and then you are normalizing layer.dense, normalizing layer.dense, normalizing. Okay, so these are two different ways of defining. Either you can call the sequential API and start adding the layers to it. This is one way. Another way is, you can again call the sequential API. Inside it you can define it as a list of values, and there in that case you don't need everything else. You just need the layer.dense and you can define. Okay, so this way you can call both the ways you can use, whichever is suitable for you. Now in this layer, you can say in this neural network, this seems to be a complex neural network where you have 600 neurons, 300, 150, 75, 7. Again, you are free to test with these numbers like how we have tested before. Whichever gives you the best result, you can keep it. Next is you will call the model.compile. You will specify the optimizer as we have seen in our experience. Adam performs better, so I'm gonna straight away choose Adam. If Adam is also not giving me best result, I will choose Adamax. I will add AX here, Adamax. Okay, so that you can do. And loss function you have to choose, because we are classifying. Classification has different loss functions. Regression has different loss functions. If it was a regression problem, I would have chosen root mean squared error, or mean squared error, or mean absolute error, mean percentage error. That way you can choose. Mean squared error is the most used one. Because it's a classification problem, I'm choosing categorical cross entropy. Okay, entropy means randomness and a mixture of various classes into one. So cross mixture categories. So that is what, again I will explain this in depth, but for now just know that this is the loss function for the classification, and the metrics we are measuring is accuracy. Okay, when you do all this, when you define the compile, now you only have to fit the model. But there is another catch. Before fitting the model, remember in one of our classes we said all the values for a neural network multi-layer perceptron have to be between 0 and 1, right? Remember, that's why we are using the standard scaler. We want every value to be between 0 and 1. So you have to first do the transformation, bring down the values, all bigger values to 0 and 1, and then you can go ahead and fit the model. When you fit the model, you can provide the data, validation data, batch size epochs, here callbacks. This is where I'm using the early stopping. Okay, that whatever I have defined before. Verbose equals to 0. Verbose equals to 0 means 0, 1, 2. You have different values. You basically are enabling the logging part. And then you're predicting and choosing the best index. Argmax will allow you to choose the index. This we have learned in NumPy class. Okay, so for each index value, whatever the value you have obtained, that you are selecting. And these two, notice that yval_pred, you are passing here yval_pred and versus yval and calculating the accuracy. Okay, so multiple times I'm doing, that's why I'm using k-fold. Okay, for various runs. When you do, finally you can print the accuracy, and as you can see, here, so it has run for the k-fold. First fold accuracy was 96%, second fold accuracy decreased a little bit, but for the next run it increased. It increased and then fluctuated. It doesn't seem to be improving actually. Okay, it's improving, but slightly, very very minor value it has increased at k-fold 8. For 8th run, it has increased, accuracy has gone up by 0.96311. Okay, overall mean accuracy is calculated. Finally, overall mean accuracy is 96%. That means neural networks have done good job in calculating the accuracy on this tremendous big data set. By the way, this cell has taken how many hours? At least 3 to 4 hours to run. Morning 5 to at least, I think it stopped just few minutes back, 9:30. Okay, anyway, so that is because the data set is huge. 40 million records are there, right? So that's why, or 4 million records, I don't know how many. So many records are there. Okay, so that's why it's taken too much time. Anyway, so this is how you can use the multi-layer perceptron, and this is the scalable way. If you want to write scalable code, you have to use Keras. Okay, if you're gonna use multi-layer perceptron, I would say recommend that you use Keras, and use these approaches to compress the memory, reduce the memory. Okay, for all your exploratory data analysis. Here we have not done much EDA because the data is too huge. For each plot it will take 1 hour maybe, because it has to go through so many records before coming up with the plot, right? So that's why we have skipped that part. We have straight away gone to the machine learning part. But you would be ideally doing the picking the samples and doing the EDA part. Is this understood and clear? Only for yeah, correct. For all the neural networks, this is the beauty again. For all the neural networks, whatever you saw just now is the same type of steps you will do. Same type of steps, is just that neurons will differ, shape will differ, these values will differ, but the methodology is the same for all neural networks. Same model compile, same process running, everything. So if you learn this once, you will it will help you a lot. Okay, yeah, so I hope that answers your question. Is that what you are trying to ask? Okay, anytime you work on neural networks. Mhm, go ahead. Mhm, mhm. Correct, correct. That's why we can't parallelize. Okay, so that's why it's called as sequential API. Although there are other models also, we'll talk about it. But this is the basic one, most basic and most I would say easiest one to understand. Okay, and the very nature of the calculation is the output from one layer has to go to other layer, right? As an input. So that's why we can't parallelize this. This process can't be parallelized, so we have to wait for it, but the process remains the same. Yeah, correct, correct, correct. So you can use how many number of layers you want. See, another advantage I'll tell you. If you use any classical ML on huge amount of data, no, it may not be able to capture the complex relationship. That is one. Second thing, notice another thing. Where have you done the feature engineering here? The only thing you have done is handled missing values, okay, and label encoding, and the one more thing is you have transformed standard scalar using standard scalar. These are the only things you have done. If I had to use a classical ML, I had to do extensive feature engineering. I had to do understand I had to run EDA, understand, do handle the skewness, basically bring the data into some sort of transformation. Lot of things I had to do, right? All of those things are not required by neural networks. They will figure out, neural networks figure out things on their own. So that's why see this as a advantage on huge. If you're using huge data, then if you want to get rid of feature engineering, then you can use this. You all basically the only things you have to do is handle missing data, okay, label encoding, and transformation. Only three steps. No feature, no other additional feature engineering steps are required. So that is another advantage, and okay, of using neural networks. So this way you can use it